In this video, we will observe the effects of light refraction across various surfaces and in differing weather conditions. We'll look at some observations over water, land, and from home. These observations demonstrate how upward light refraction, which makes distant objects appear lower than they actually are, is a common occurrence that is seen day after day in various conditions throughout the year. Although temperature is not the only factor with these observations, generally, when the layer of air near the surface is warmest and the air temperature decreases from there with gain in elevation, distant objects will typically appear to sink. What's more is, they seem to sink exponentially with increase in distance from the viewer. This atmospheric effect can make flat or horizontal surfaces, where no physical obstruction is present, appear convex by creating apparent obstruction of distant objects. And curved or sloped surfaces with some physical obstruction appear more sharply curved and the obstruction greater due to this sinking effect. This effect can even be witnessed over ice, and over water in the evening. First, we will explore observations over small bodies of water. These observations are conducted within 1,000 feet from the viewer and with a viewing height of approximately 2 inches above the water surface. The goal is to get a relative viewing height to the distance of objects that equates to an observer looking over an ocean or large lake at a distant boat or building. For instance, viewing objects at a distance of 600 feet away from 2 inches off the ground is equivalent to an observer viewing objects at 6.8 miles away and from 10 feet above the water surface. We'll use the scale of 1 inch equal to 5 feet to scale down our observations and to see how they correlate to observations over large bodies of water at the same relative distance. As we've pointed out before, curvature cannot be the cause of obstruction in any of the following observations. At a distance of 1,000 feet on a sphere of our given radius, there would be only about 0.3 of an inch of curvature drop, and there can be no obstruction due to curvature. From a viewing height of 2 inches, the geometric horizon would be over 2,600 feet away. So, all effects witnessed in this video cannot be caused by the curvature of the Earth. These effects are all apparent and caused by the surrounding air. Here is a calm day on the lake where we sail an RC boat out. Here, the RC boat is around 300 feet or so, and it is approaching the apparent edge of the waterline. As the boat sails beyond 300 feet from the camera, the boat begins to disappear from the bottom up due to the inferior mirage. As it travels beyond 500 feet, most of the hull can no longer be seen. For this next test, we'll take our RC ship out to just under 1,000 feet from the observer. Here is a look at the size of the RC ship in inches. Here is the ship at around 300 feet from the observer and sailing beyond. By 700 feet or so, the hull of the ship is no longer visible. And as the ship travels just beyond 900 feet, only the very top inch or so of the ship's towers are visible. Observing from 2 inches above the surface at a distance of 900 feet is the equivalent of an observer viewing from 10 feet above the surface at a distance of 10.23 miles. In looking at an object 10.23 miles away, from a viewer's height of 10 feet, the globe model predicts that only about 3 feet should be visible for a distant object that's 30 feet tall. What's interesting is that this inferior mirage, which doesn't allow the light from the bottom of the RC ship to arrive to the viewer, is blocking nearly the same relative amount of the ship that should be blocked by curvature on a sphere of our given radius. Only the top inch or so of the RC ship is visible by the end, which would be equal to 5 feet to scale, closely matching what is witnessed over large bodies of water under certain conditions. Although very common, this sinking effect does not always occur. Different days produce different results. On days when the water is cooler than the air above, and the air temperature increases with the gain in elevation, we're typically able to see distant objects in full, up to a certain point. When this temperature inversion occurs, the light from distant objects is normally able to travel to the viewer in full. And when the temperature inversion is steep enough, the surface can even appear concave. Here are 2 different days looking at objects placed 600 feet from the observer and viewing from the same viewing height of approximately 2 inches above the waterline. On this day, when the air temperature increases with gain in elevation, we're able to see the distant objects in full. And on this other day, when the air near the surface and air above it are about the same temperatures, but the water is just a bit warmer, we witness upward refraction as the light from the bottom of the distant objects does not arrive to the viewer. We have to raise our viewing height to receive the light from the objects in full. The air on this day displaces the distant objects, making them appear to sink, and also seems to enlarge them. In reality, the objects are likely higher up, but we're looking down into the water to make this observation due to sinking refraction. This effect creates an apparent edge to the waterline that appears much closer to the viewer than where the waterline actually is at the opposite shore. Here is another look at each day. Although we're sometimes able to see distant objects in full on days with a temperature inversion, other times we're not, as compression can make distant objects still seem to disappear bottom up. As the boat reaches 600 feet from the observer, only the sail is visible. We have to raise our viewing height to see the whole of the boat. These ever-changing views of distant objects have been captured by various observers over the years. And these effects we witness across these small bodies of water seem to mirror what is observed over greater distances, presented by channels like BMLSB, Wide Awake, The Plain Truth, and many other observers in this realm of research, some of which are linked in the description below. Next, we'll show some observations from our land in the Colorado mountains. The surface we are viewing across is not perfectly smooth and definitely has some undulation to it, but during the evening and morning hours, while the air and surface temperatures are mostly evened out, we're able to see distant objects in full. During the day, however, the air layer at the surface will pretty much always be warmer than the air above it, and the temperature will decrease with gain in elevation from there. And so, sinking refraction occurs. In this observation, the cars are placed 45, 60, and 75 feet from the viewer, and we're viewing from about half an inch above the surface. This evening, the light from each of the cars arrives to the viewer in full. During the day, however, the objects appear to sink into the surface, with the most distant car sinking the most. We have to raise our viewing height to receive the light from the cars in full. Here is a test with a small amount of obstruction caused by the undulation of the surface. Even around sunset, when the air temperatures are evened out, we have to raise our viewing height to see the objects in full, as they are being blocked by the physical surface. During the day, the objects appear to sink as the obstruction of the surface is exaggerated. Only the very top of the yellow car is now visible, and we have to raise our viewing height more than the previous evening to receive the light from the distant cars in full. Next, we'll look at some scaled observations of a distant highway and house. Daytime temperature highs reached the 40s and 50s in these observations. The highway and house we're viewing are 1.8 and 1.9 miles away, respectively, and we're viewing from just under 6 feet. In order to closely scale this, we'll imagine a scale of 1 inch equal to 10 feet, putting our small scale representative objects at around the same relative distance to the viewer height. On the large scale during the evening, cars can be seen in full for the most part. But during the day, only the very top of the cars are visible. The same effect occurs on a small scale. This evening, the Hot Wheels car is seen in full, but during the day, only the top is visible. Here is a semi-truck one evening, and a semi-truck during the day, and another small car during the evening, and during the day. Last, we'll look at some observations conducted from home, both in a garage and from a living room floor. At distances of 35 feet and less, these tests are conducted at an even shorter distance than the previous observations. So, they require a difference of temperature from the indoor and outdoor environments of around 30 degrees Fahrenheit or more in order to witness noticeable results. You can create both increasing and decreasing temperature gradients by keeping the surface warm and cooling the air above, or vice versa. Each will present varying results. Here, we placed a few earrings and small rocks about 35 feet away from our viewer, which has a viewing height of about 1 inch above the surface. The indoor environment temperature was around the 70s in degrees Fahrenheit, and the outdoor environment was in the 30s. As we open the garage door a bit and let cold air in near the surface, the objects appear to sink into the surface, which also appears to drop. Here we speed up the footage. And here we close the garage door. As the air in the room evens out, the light from the objects arrives to the viewer in full. Here is an observation from a living room floor. Notice the reflection of light on the surface. When we open the patio door, the same sinking effect occurs as the reflection and the bottom of the objects are no longer visible. The reflection then comes back into view when the door is closed. Here's an observation where we placed 3 small buttons at 14, 16, and 18 feet from the viewer. As we open the patio door, the buttons appear to sink, with the most distant button appearing to sink the most and the nearest button appearing to sink the least. Also, the original horizon, which was caused by the floor meeting the far wall, now appears closer, therefore lower in the field of view to the observer than it was at the beginning of the test. All of these tests and observations show us that there may be an alternative explanation for bottom-up disappearance of distant objects. Many people attribute this disappearance to curvature of the Earth, but we've seen in these various observations that the surrounding air is capable of making flat or level surfaces appear convex by displacing the light from distant objects and making them appear to sink. Regardless of the shape of the Earth, it's clear to see that this ever-changing effect of light refraction makes certain explanations not so clear-cut. Thanks for watching. There's more to come soon.